Okay, hi everybody. My name is Neil Stevenson. I'm Principal Architect at Hazelcast. I'm going to talk today about continuous querying and a little bit of a demonstration. So, continuous querying, kind of questions people want to know in any kind of trading platform. When did we last sell something? And how much have we sold today? These are kind of really basic what-if questions. And if you look at them in detail, what that's kind of asking for, where did we last sell? Well, that's a last state kind of question. How much have we sold is a derived state question. So the top one is something that you might be satisfied from data storage, data grid, on terms of state, and the bottom one from stream processing in terms of derivation. And the thing you really want to do is do them both in one place. So if we have a look at traditional solutions to this, typically if you were like a stock market trading system, you would be receiving your trades coming in from the outside world, from the stock markets, obviously. What people tend to do is they'll store these in a database for legal and audit reasons, for settlement, all sorts of reasons. They kind of store them in a database. And then they'll make those trades available on screen in a web server so that somebody can see, what's the current price of X, Y, Z. And then typically what they want to do is this kind of what's the volume of trading today? What stocks have been selling well? And if you run that across a database, that in some sense is a table scan. It's not the sweet spot for what a database does well. So what you've essentially done is you've turned a stream of events into a batch. So you've put the brakes on and there's a latency to getting the result out of the database, which could be hours depending on how much data you've got, which if you're doing any kind of insights is hopeless, miles behind what's happened in the world, and all your competitors have jumped on it sooner than you have. So what we want to do with Hazelcast here is as we pull in this data in, we can simply load that data into a Hazelcast grid. We can make a day's worth of trades, 10 days worth of trades be visible. As trades come in, we just make them immediately available on the grid and therefore immediately available to grid clients, in this case, a web server. But at the same time, we can be running the streaming engine on that same data and produce running totals at the same time as we're doing the ingest. So we do aggregation and storage at the same time, meaning we get the aggregated results at the same time as the thing they're aggregated upon. So essentially you get the running totals updated all the time. You'll still do persistence probably. It's just not kind of relevant to this part of the solution. We've separated out the calculation from the longer term storage. So the way we do this in Hazelcast, we call our stream processor, essentially it's a pipeline. If anybody's ever used like a Unix pipeline, it's a similar kind of concept. You have a step that passes data to another step that passes data to another step. So, LS pipes to grep, pipes through awk, etc. Each step is simple. So we're reading in from a Kafka topic. We're doing a reference data lookup. So for our trades, we're checking that the stock symbol is not bankrupt because we're not interested in those stocks. So that's a lookup to data that's in the memory store. We're then doing a bit of grouping, a bit of aggregation comes off the back of the grouping. So we want to group all the trades with the same stock symbol together. We want to aggregate them to work out what the trading volume is. And then we store that data in Hazelcast as well. So that is available to the web client. Here's a little bit look at the code. We mentioned earlier that these are kind of essentially primitives. So it's 5 steps. So that read from step, basically use a predefined source and you just give it a name of a Kafka topic. So it's a queue to read from. The enrichment step, you just give it a name of a map in Hazelcast and check the status of that stock symbol in the map. That's just a reference data lookup. Grouping is straightforward. That's essentially finding a foreign key in the data to become the primary key for the next stage. And then we do a rolling aggregation. So rolling aggregation is one item comes in, one item goes out. So every time a trade comes in, we update the running total for that trade, for that stock symbol. There's other kinds of aggregations as well, where you can do it on Windows and say, produce output every 5 minutes. But in this case, we're just doing it for every trade. We're just keeping track of the grand total for the number of trades, how many there've been, how much the trading volume is. So that's the price times the quantity, and what the last price is. And the last step of our pipeline is we just write this into a map. If you're an SQL person, you could code it SQL style. This isn't the exact same query, but it's just showing you can do these things in an SQL style manner, if that's what you prefer. So conceptually, what we're saying is we've got trades that are keyed by their trade ID, which is just some sort of random number. We're reading it, passing it through our processing pipeline, and out come the results. But the reality is that Hazelcast is a clustered system. So we run this across multiple nodes, multiple machines, in this case, 2 machines. So we have 2 copies of our processing pipeline. We can process twice as fast. If we had 40 copies, we could process 40 times as fast. So scale up, dead easy. So given the background, I'll do a live demo. So this is my input source. I have just a series of trades on a Kafka topic, on an input queue, essentially. They have various fields, a trade ID, some random number, a timestamp, and what matters is a stock symbol, a price, and a quantity. So I load that data into my web application, and what we'll see is these trades are coming in at a specific rate. In this case, it's 300 per second, but it can be any kind of rate at all. As we know, it's all kind of nice and scalable. Every time a trade comes in, we'll see these numbers flash green or red as the price is going up or down, and we'll see the running total being changed as the trades are coming in. So we have a live view of the running totals that are coming out of the aggregation. If for some reason we're interested in one of the symbols, we can expand it out and see, well, here are all the individual constituent trades that constitute that running total. And that might be a thing you wish to do, if you need to find out, has there been like a lot of volume on some stock? Is it one big institution doing lots of large purchases, or is it lots of little purchases? Those kind of things are things that you want to do. Now, obviously, in a real system, you're kind of concerned with monitoring as well. So if we look at my Hazelcast grid has got 2 members. I can go and look at my processing job, my aggregate query. This is a visualization of the code I showed you earlier. And I can select my map stage, and I can see that 600,000 records have come in and 570,000 records have gone out of that stage, because I'm filtering out some records. I'm dropping the ones that are in bankrupt status. And that dumps that results into a Hazelcast map. So I can see in my grid, I have about 600,000 trades. That number will go up now, 608,000. I have 3,000 stock symbols. And because of that, I've got slightly less than 3,000 aggregation results, because I'm filtering some out. And if I want to be nosy, I can actually look at the aggregation results. I can just run an SQL query, and that will tell me there's our one there, TOPS, TOPS. There have been 176 trades. That's the total trading volume, whatever, and 2,500 is the current price. So that's just updated every time trades are coming in. So that's the result of the aggregation. Every input causes one output. Now, I'm going to ask my PAS layer to scale up. So currently I'm running a grid of 2 machines, and I'm going to ask for a grid of 3 machines. There we go. That's how you do scaling on the cloud. Not wonderfully exciting, but it does this job. So if I go to my dashboard, kind of one of the things I want to see maybe is these kind of ad hoc queries. And this is where, so these queries here, these are all just the kind of standard stuff or pre-built ones. This is where we're kind of doing them on demand. And I might want to say, let's go and do a left join my KF trades, which is a data source that's external to Hazelcast, join it on symbols, which is data source that's internal to Hazelcast. So it goes and scans that Kafka queue from the outset and does a left join on a Hazelcast map, and there's my result. So there's how we see stock symbols. That stock is in deficient status, all the other stocks are normal, and so on. And if we go back to our Hazelcast map, Hazelcast system, and we look at our cluster, we now have 3 processes in our cluster because the PAS layer has added an extra one. And all of that happened while we were working. We just scaled up while we were using the system, and now we have 50% more capacity. So we could store more days worth of trades, or we could cope with a higher volume of trades. And it's not difficult to imagine that this might not be trades, this might be e-commerce purchases or a number of things. And just a last piece here, that Hazelcast Management Center is feeding other monitoring tools. If you've got other monitoring tools, it integrates into your cluster. So in this case, we can see the member count on another monitoring tool and so on. Just back to my slides to finish off.
Neil, if I can actually interrupt you for a second. So it basically looked like, if you can pull that monitoring system back up, from what it looked like as we added the 3rd node, you literally see the performance drop on the other 2 after that node kind of came in balance. So as we add more nodes, that the thing we can expect to see every single time. We can just literal scale. As we add more nodes, we see everything drop and everything just balances nicely.
Yes, so that is exactly what balancing is doing. So if you remember, when you're doing that routing by stock symbol, if you're keeping all the running totals for stock AAA, all the trades for stock AAA have to go to that node. And all the trades for stock BBBBB have to go to a different node, and all the stocks for CCCCC go to a different node. When you add another node, you move the accumulators, the counters about, and you have to change the routing because now you've split it into 4 instead of into 3. So basically, you take the foreign key and you take essentially the hash code off that and modulus it by the number of nodes to work out which node is responsible for keeping which running total.
Okay, so you're doing a rebalance of the entire data platform as after the node has been seeded effectively.
Yeah, and it's the same if a node goes away. It's okay. No scale up, scale down. If you're doing that kind of you can do it reactive based. You can look for CPU count or throughput or whatever if you're getting close to your SLAs. If you're asking your cluster to do more and more, then you're probably going to need to scale it up to make sure you hit your SLAs. If you've got a busy weekend, you can scale it up. If you do extra processing, you can scale it up. If you've got a quiet time, you scale it down. All that happens is it just rebalances the routing of the processing across the available nodes, and it rebalances the data that's stored on the available nodes. And fundamentally, a lot of that is about the speed of the network. If you had a 1 terabyte cluster across 10 nodes, well, it's 100 gigabytes on each. So to rebalance, if you add one, you've got to move 1/11th of a terabyte across the network, and that partly depends on the speed of the network card and what else the network is doing.
Quick question, kind of based on that. Are there any elements built into the Hazelcast, software structure to detect, like if a specific node within the cluster is experiencing higher throughput due to a specific, like using stock stuff like GME, like GameStop trading like mad, right? If you have an instance like that come up, is there any way to kind of automatically like expand clusters, or is there anything for kind of that hot data detection within a node that Hazelcast has?
That's really more of a PAS layer kind of thing to say, well, this particular node has got higher volume than others, because if, say, your traffic was spread across 10 nodes and you go to 20, well, you would expect that would half the traffic on each. But if you've got one particular hot stock, then that's not going to be the case. You've just moved all the other data away, but all the processing is on one. So that's where you've got to be careful. That's where you kind of need monitoring to do that kind of lights out auto scaling up to a point. If you're getting busier, add some more nodes, but you need to make sure you'd have that feedback. Is adding more nodes actually helping? Because it's pushing your hardware cost up. So
yeah, that really comes down to the application too, right? Very application specific, and the application developers need to be aware of that. Okay.
Yeah, I mean, fundamentally, that you're trying to get a perfect balance, and that'll never happen. There'll be a deviation 5-10%, and you don't really care. In a grid, you don't really want hot spots. Cold spots are bad as well, but they don't kind of really hurt you. So that rebalance does as much as it can to limit the work, but it's not magic. If you've got 100 data records and all your updates are the one data record, it wouldn't help to have 100 nodes.
Cool. Now your demo also showed what looked like ANSI SQL to query some of the data. Do you have any other mechanisms to actually get into that data? Any other querying technologies?
Yeah, well, you can. It depends how it's stored. In my example here, I'm storing it as JSON, and you can code it in various kind of ways depending on your end technology. So you can do a query against the JSON object. You can query against. Essentially, the grid needs to understand the internal structure of the object in order to be able to query it. So if you were trying to query on an image, that's not going to work particularly well, but I'm sure you could figure out a way to do it. Fundamentally, most of the data in a key value store has got a predictable structure. It's a person record. They've got a first name, a last name. They've maybe got a social security number. They've maybe got a postal code. It's not usually totally random data. Well, sometimes you might have you might be allowing people to upload profile pictures. You might have a user account and they can upload an avatar. So it can be that if you want. So for that stream processing, the main part of that demonstration was predefined analysis, because you're going to know what you want to do from day to day. But you can do those ad hoc queries, and essentially they're the exact same as far as the system's concerned. One is just kind of pre-launched on my demo, and the other one I'm just typing in at runtime. And if you're an end user, you can be querying data that's in the grid or querying through, and you don't know, and more importantly, you don't care. You're just querying it, Hazelcast getting it back for you. You've got a nice, simple, standardized interface, and that's all that you want.